Okay, so today we are going to talk about trapezoids and kites. Um, so today you'll be able to apply properties of trapezoids and you will be able to apply properties of kites. Um, so whole bunch of new vocabulary in this one. We're just going to do a brief fly through of these. Trapezoid, that's quadrilateral with only one pair of parallel sides. Typically, you see them, they look somewhat like that. Um, not somewhat like that. More like ah, more like that where that line's straight too. Um, where the top and bottom would be parallel. So that's typically how you see a trapezoid. The bases of these trapezoids are going to be either of the two parallel sides. Typically, you see these noted as like B sub 1, B sub 2. Those are the two bases of any singular trapezoid. Then we also have the legs of the trapezoid, which those are the sides that connect the bases, these little askew, um, lovely askew sides. And then base angles are going to be the angle formed between the base and one of the legs. So this shaded piece could be a base angle, or this shaded piece could be a base angle. Even these two up here could be base angles, depending on how it is shown in the given example, because they are also connected to a base and a leg. An isosceles trapezoid has one line of symmetry. So, line of symmetry is something we haven't really talked about yet, but essentially, what a line of symmetry is it's a line that you could fold a shape on, and it would be the same on both sides. So, an isosceles trapezoid, pretending once again that I can draw, would have a line of symmetry cut right down the middle because you could fold it in half like a piece of paper and it would match up perfectly. Um, and that would be the only type of trapezoid that would have a line of symmetry. Typically, when we talk line of symmetries, we're talking about all the shapes at once. So, just for like another reference, like a square, if we had a perfect square, it would have a whole bunch of lines of symmetry. So, you could do lines of symmetry diagonally, straight up, straight down, left, right. So, it would have four lines of symmetry. So, for a shape to only have one line of symmetry is kind of, I don't want to say rare because most don't have any, I guess, if you want to get technical, but most of our typical shapes have more than one line of symmetry. Squares, rectangles, um, kites, rhombuses, most have more than one, but an isosceles trapezoid only has one, which is one more than most trapezoids. Now, the mid segment of a trapezoid is the line connecting the midpoints of both legs. So let's just pretend this was our midpoint on each leg. So the mid segment would run between those, um, just like our mid segments we had done before when we were talking about, I believe we did them in triangles and we also did them in regular parallelograms as well. Not regular parallelograms, but like standard parallelograms. Okay. Then a kite is a quadrilateral with two pairs of consecutive congruent sides. So it only has two pairs of consecutive congruent sides. So a square would not be a kite because it doesn't have two pairs of consecutive congruent sides. They have to be different. So, like, a kite would look like this, where we have two sets of congruent sides, but they are not congruent to each other. Okay. Or adjacent. I guess your congruent sides have to be adjacent, so they have to touch each other um, at the vertex, kind of on top and on bottom. So that is what a kite would look like. All right, continuing on. So we have rules for isosceles trapezoids. Our first rule is If the trapezoid's isosceles, then each pair of base angles are congruent. I think it would be are, not is. That'd be a question for Ms. Roberts, I'm guessing. So if a trapezoid is isosceles, then each pair of base angles is congruent. Yeah, that's got to be an R. R congruent. I'm saying it's an R in my expert language arts opinion. So that means GFJ or GFJ and HJF would be congruent. And then at the same time, HGF and GHJ would also be congruent. So your two base angles that share the same base, those are going to be congruent to each other in an isosceles trapezoid. If a trapezoid has one pair of congruent base angles, then it is an isosceles trapezoid. So if one pair of base angles are congruent, if one of the pairs are congruent, then that means the other pair is congruent as well. And that kind of falls along the same justification as when we were talking about our perpendicular bisector or our bisectors, that the distance between those points has to be the same. It kind of follows those same rules in a way. Because essentially, if we think about it, so we have two parallel lines. And if we left on the same bearing from each line, so let's just say we were going from left to right. And if we left on, let's use the red, and let's just say we left at 45 degrees in each direction, then if we went 1 meter, we'd be the same relative distance. 2 meters, we'd be in the same relative position. 3 meters, 4 meters, so on and so forth. And they would hit this second parallel line at the exact same time. So they would be the exact same distance, which would make them the exact same angle when they eventually hit this, the same angle they would hit at. It's kind of goofy, but it works. It's a cool little fun fact. So, oh no, I didn't erase that part. So, continuing on, a trapezoid is isosceles if and only if its diagonals are congruent. So, the diagonals going from opposite vertexes have to be congruent. So, RT would have to be congruent to QS. They would have to be the same length for this to be an isosceles trapezoid. And that's a good, really quick test to figure out if the trapezoid is isosceles. So let's get into some real world examples. So each side of the basket shown is an isosceles trapezoid. They give us a whole bunch of information. They say angle JML is 130. They say KN is 6.7 feet, and they say LN is 3.6 feet. They want us to find the measure of MJK. So, MJK. Yeah, cool. So, they want us to find this angle right up here. And how we would go about finding that is we know JML is 130. This is an isosceles trapezoid, which means KLM is also 130. And since it's a quadrilateral or a four-sided figure, we know that all the interior angles are going to add up to 360 degrees. And we know angle MJK and angle LKJ are going to be congruent to each other. And the cool thing about isosceles triangles is if we take a base angle from each base, like JML and MJK, we know they have to add up to 180 degrees, which we'll get to the reasoning behind that. But essentially, for this problem, not knowing that fact, what we would say is, okay, we know it needs to add up to 360. We know we have two of these 130 angles, and then we're going to have two of these unknown angles. So we would say 260 plus 2 times unknown, or x, is going to equal 360. We would go about solving this, and we would say 2 times that unknown quantity is going to be 100 degrees. Then we would divide by 2, and we would find out that our missing angle is 50 degrees. And so when we have an isosceles trapezoid, no matter what we do, these two angles are always going to be 180, and these are always going to be 180. Since we're working in multiples of 2, we can divide by 2 and just work on that one side, trying to get to 180. If you prefer to just work to 360, you can do that too. But if the dividing by 2 trick works for you, then it works for you. So anyway, long story short, 50 degrees would be our final answer. So now we're dealing with the same trapezoid, but they want us to find MN this time. So they want us to find this little stretch here. Now, if I remember correctly, they had told us in the last one, oh, they're going to give us different information here because they're tricky. Okay, we'll work with the information they give us, I guess. So they say KN, this red section, is 6.7 feet. And then they say JL, so I hate it when it does that. So they say JL, so this whole diagonal here is going to be 10.3 feet. So essentially, we're taking the whole diagonal, which is 10.3. We're going to subtract this NK section of 6.7, and that's going to give us our remaining blue section of MN. And our final answer will be 3.6 feet, which we could have also just looked back and said, oh, look, it's 3.6 feet from the previous problem. But, whatever, fancy stuff. So now on this question, we are looking for EFG. This is one that you would do on your own in class, but for funsies, I will do it right now. So they tell us that this whole angle here is going to be 124. I know 124 plus this angle that we're trying to find is going to equal 180. So 124 plus unknown is going to equal 180. So my missing angle is going to end up being 56, or C. As we continue on, we're looking for IH this time, and they've changed up our numbers on us. Do they give us IG? That'd be really cool. Okay, so our whole diagonal is going to be 14.1 feet, and the bigger section of our diagonal is going to be 9.8 feet, which means we need to do 14.1 minus 9.8, which will give us 4.3 feet. All right, so now we get into the fun graphing part that we all love. Believe it or not, I am going to say we should use GeoGebra for this. However, I'll tell you another way you can do it. So essentially what this problem says is we are trying to prove that this is an isosceles trapezoid, which is all fine and dandy. The best way to do that would be to calculate the distance for these two diagonals to determine if it's isosceles. If both distances on the diagonals are the same, then we know that this must be an isosceles trapezoid. So we could do it one of two ways. First way would be Pythagorean well, you could use distance formula, which is gross, or you could use Pythagorean's theorem, which would make two right triangles using the side lengths to figure out the distance on that diagonal. So this one has a height of 5 with a 5. So we would have 5 squared plus 5 squared equals that missing side squared. So we would end up with square root of 50 equals our missing side. And if I did this second triangle, I would go down 2, right more, which would be down 2, so it would be 2 squared plus 3, 4, 5, 6, 7 plus 7 squared equals c squared, which would end up giving me the square root of 53. Uh-oh. It's not looking like it's going to be isosceles, but just for good measure, we'll go take a look real quick at the old GeoGebra. So I've already set up our trapezoid the way they had it set up. I'm just going to show you how I would do this in GeoGebra. So I would graph this using the polygon tool. Then I'd hit my segment tool. I draw in my diagonals, connect B to D and C to A. Then I'm going to go back up top. I'm going to find my distance or length in the measure segment. And I'm just going to click on each of these individual lines. And I see right away that these are not the same distance. So one of them is 7.28 blah, blah, blah. And one of them is 7.07 blah, blah, blah. So these are not the same, which means that this is not an isosceles triangle. All right. Now, if we go back to the presentation, there it is. We would say, no, exclamation point, exclamation point, exclamation point, frowny face, maybe even a tear for good measure, because we are not happy that this is not an isosceles trapezoid. Okay. So really, GeoGebra to me is the easiest way to do it. I can do it using Pythagorean theorem pretty quick. So that's not a problem for me. However, I think for all of you that are less practiced, one, it would be really good practice to use Pythagorean's theorem there. But at the same point, it's probably going to be more accurate for you to use GeoGebra. So I would recommend using GeoGebra. All right. Now, trapezoid mid-segment theorem. So we have some really cool things we can do with trapezoid mid-segments. And the main thing that I think is really cool is, well, let's cover the less cool part first. So when you have a trapezoid mid-segment, so you take the midpoint, you connect them, that ends up making 3 parallel lines, which I guess is cool. However, well, it makes 3 parallel lines, and then each side, the 2 segments are congruent because they are the midpoint of each segment. So that's cool. That's all fine and dandy. The really cool part to me is this chunk right here. So what this says is BE, this segment, is going to equal half of AF plus CD. So if we add the biggest segment and the smallest segment and we divide by 2, we're going to get that middleist segment, aka the mid segment. So I don't know why, but like the average and how that works out, I think that's kind of cool. That being said, probably going to lead to some algebra, which I know you all love. So let's give this a shot. First of all, middleist segment in the middle. So we know our littlest segment plus our biggest segment. So littlest segment plus the biggest segment divided by 2 is going to equal that middleist segment of 30. Now, to solve this, what we're going to want to do is we're going to want to times both sides by 2, which leaves us with 60 equals 20 plus x. Subtract 20 from both sides, and we find out that our biggest segment, or x, is going to be 40. I think that's pretty cool, personally. The other way, if you're good with like your multiplication facts and stuff, you could say, okay, I know, let's erase this real quick. I know this plus this, so 20 plus x is going to equal the middle segment times 2. 30 times 2 is 60. So what plus 20 is going to equal 60? Well, that's 40. So you can think through it that way too if you don't want to set up that equation every time. But I think it's just kind of a fun little trick. So this is where you would give this a shot on your own during the presentation, but we're going to do it together since this is the video. So our biggest segment is 25, our middlest segment is 18, and we don't know what our littlest segment is. So me personally, I would say, okay, 25 plus x is going to equal 2 times my middlest segment, which is 18. So 36 equals 25 plus what? Now I could solve this more, or I could just say, yep, it's 11. 25 plus 11 is going to be 36. Yay, math. All right, cool. So now we're talking kites. If a quadrilateral is a kite, then its diagonals are perpendicular. They are just perpendicular. They are not perpendicular bisectors, like we saw with rhombuses and squares. Not perpendicular bisectors. They are just perpendicular. Okay. But since they are perpendicular, we have 4 right angles, which appears to be a perfect storm for some Pythagorean theorem goofing, which is awesome. Love some Pythagorean theorem goofing. Next theorem is if a quadrilateral is a kite, then exactly one pair of opposite angles is congruent. Only one pair. One pair of opposite angles is congruent. And that would be the angle that is between the two different side lengths. So the angle between the congruent sides on each end, that's never going to be the same. However, the angle where they meet up, that is always going to be the same. So what I'm saying here is this angle is between two congruent sides. This angle is between two congruent sides. Never, ever, ever going to be congruent. Your congruent angle is always going to be between your two sides of different lengths. And there's a complex triangle reasoning for this. It loops back to that side angle side theorem that we covered before, but you know, I'm sure you guys all want me to go into more depth, but I'm not going to. So if quadrilateral WXYZ is a kite, find the measure of ZYX. So we want to find this measure right here. So the nice thing is they gave us 2 measures, and I know this angle and 121 are congruent, which means I have 121 for 2 angles. Now, I also know all 4 angles added together are going to be 360. So I know if I add 121 plus 121 plus 73 plus X, I'm going to get 360. So that being said, I can add some of these. So 2 of those, which is 242. 242 plus 73 is going to be 222, 245, 315, 315. So 315 plus X is going to be 360. Now I subtract 315 from both sides and I wind up with X equals 45 degrees. So that sum of interior angles not going away. That's a tool that we're going to use for at least another week. And you will see it as you go on in future math. That's actually one thing that I have used and I think is kind of fun. So continuing on, if MNPQ is a kite, find NP. So we need to find NP. What? We have no angles that help, or we have no measures that help us with that though. Oh, but wait, we have a right triangle with two side lengths on this, and of course NM and NP are congruent. So what we're going to do is we're going to do some Pythagorean theorem goofing. So we're going to take our two shorter sides that are not opposite the 90-degree angle, and we're going to say a squared plus b squared equals c squared. So 6 squared plus 8 squared equals c squared, because Pythagoras says so, which means 36 plus 64 equals c squared, which means c squared equals 100. We take the square root of both sides and we end up with c equals 10. So that side is 10, which means this side is also 10, which is delightful. So NP is 10. Yay. Continuing on, all right, this is one you do on your own. However, we are not in your own territory right now. So we're trying to find this angle just like we did a hot minute ago. 130 for this because these are congruent, of course. And we're left with 260 plus 64 equals 324. So 36 is going to be our missing angle. Now, once again, we are going to try to find KL, just like we did a few minutes ago. And in order to do that, we're going to need to find the missing side on this lovely right triangle. A squared plus b squared equals c squared, because Pythagoras says, which would lead us to 3 squared plus 4 squared equals c squared, which would be 9 plus 16 equals c squared, or 25 equals c squared. Square root of both sides, we end up with c equals 5, which, fun fact, we didn't really need to go through all of that, mainly because there are these things called special right triangles, and those would be like 3, 4, 5. So in a right triangle, if you have side lengths of 3, 4, then the next one's going to be 5. I think there's 5, 12, 13 is another set. 5 squared plus 12 squared, just to double check. Yeah. 5, 12, 13 is another set that you can always know right away as well. So that being said, this is the end of our video. Let me know if you have any questions.